Okay, so kind of a new topic now. A clean slate. I want to show you something new now. We've made just now very good use of Gauss's law. But I want to show you another way of looking at Gauss's law, a different version of it. If you will, we can call this topic Gauss's law version 2.0. And this is really sort of the flip side of Gauss's law. The Gauss's law we've presented you with so far has you doing these surface integrals, right? It is an integral equation. And as you know, actually, right, generally speaking, doing integrals and working with integrals is usually more complicated than working with derivatives. And that's really, in a nutshell, what this second version of Gauss's law, if you will, is really about. We want to ask, okay, we've been given an integral form, right, for this law, but remember, every time you have an integral, it's really the backside of doing some kind of a derivative. So we want to look for and see if there's some kind of derivative expression of this Gauss's law. And because derivatives are easier than integrals, having a derivative form of this thing might actually be very handy. Now, to do that, though, and to convert Gauss's law into some kind of a derivative, we are going to have to go back and we are going to have to use a powerful theorem from vector calculus, something that you've learned in your Math 1920 class. But it's not going to be too bad. I'm going to just, as you'll see, I'll remind you of the key theorem, and then we'll use it very quickly and come to some very powerful conclusions, and also address a very fundamental issue, which is this issue of action at a distance. This thing, right, that had Descartes thinking about his Cartesian vortices. How is it that one object can reach out across completely empty space without touching anything in between and affect another distant object? How is that even possible? Well, the differential form that we're going to show you actually answers that question. But first, let's just review the basic theorem. There's something called the divergence theorem that we're going to make use of. So the divergence theorem states the following. It says that if I do a volume integral, so now it's going to be a triple integral of the divergence of a function. You might remember this operator, the divergence. So let's imagine it's the divergence of the electric field. And I integrate that, again, as I'm saying, over some volume. And now my volume, by the way, can be any arbitrary volume. I might happen to like a peanut shape, right? I kind of like to use that for my generic volume. So here I have some kind of peanut-shaped volume, right? Some crazy-looking thing like this. And I'm going to now integrate over that entire volume, the inside of it, right? The whole solid thing. So I'll indicate that here by drawing my peanut and, coloring him in. Okay, I'm going to integrate over that entire volume. If I do that, you see what I'm doing is I am integrating a derivative. And as you know, right, the integral is the opposite of a derivative. So you might imagine that when I do the first of these integrals of the derivative of my function, usually the integral of a derivative gives you your function back again. And that's actually kind of true. That's kind of what happens. So the first integral actually gets used up, if you will, by undoing this derivative, and then I'm just left with my original function. I happen to call it e, but this holds for any function. I'm left with my original function, and then two of my integrals are left over. So what I really end up with is, when you do the full theorem, is you end up with a double integral, or what is known as a surface integral. And it turns out that it's a closed surface integral in the theorem, and it's over then just the actual surface of the peanut. I'll represent it like that in pictorial form. In mathematically formal language, what they do is they say, okay, you're integrating over some volume v. That becomes the subscript on your volume integral, and then your double integral is the surface of v, which they often will represent by, like, it looks like a partial derivative of v. What you are then left integrating is just the function back itself, because the first of these integrals here is actually undone the derivative. And if you work through all the mathematical details, it gives you back to integral actually of your function dot dA. That is the divergence theorem. I think you can begin to see, though, how this is we're going to connect this now to our physics, because this here, right, is a law of mathematics. This is the divergence theorem. I can now start to turn this into a statement about physics by using Gauss's law, because the right-hand side of this actually just matches Gauss's law. I know if I do this over a surface and I perform this integral, if I actually am working with the electric field, and that's just going to give me 1 over epsilon naught times the charge that's enclosed, Q enclosed, like so. So I've got really, as you can see, two connections here. The first connection here between these two equations, this is math, right? That's a mathematical theorem. And I have this second connection here between this one, and this is physics. Now, to turn this into something a little bit more powerful, to manipulate this so that I can actually get a differential equation for the electric field, I'm going to play two tricks. The first trick is I'm going to divide this whole equation through by the volume of my funny little peanut. So let me do that. So this is going to then be divide this side of the equation by V, divide this term in the equation here by V, and divide this side of the equation by V. So on the right-hand side now, I have the enclosed charge in my funny peanut shape, Q enclosed, and then I'm dividing actually by the actual volume of that peanut shape. That was the first trick. So the tricks are going to be that we multiply by 1 over V. That was the first one. And the second one that we're going to do is we're going to take the limit as the volume goes to 0, and we're going to take that limit in a very special way. What I'm going to do is I'm going to take my arbitrary shape, my peanut, whatever it is, and I'm going to focus in on a point that's inside that peanut. And what I'm going to do next is I'm going to shrink the volume of that peanut, right, down very tiny. Imagine it gets tinier and tinier, but what it always does is it includes that one point right there. So it's going to shrink itself right down to that point. And I'm going to imagine now what happens in that limit. So if I take that limit as the volume goes to 0, you can see a couple of things are going to happen. The first one, over on this side, I think is a little bit easier to see what happens on this side of the equation, right? If I take the limit as that volume goes to 0, 1 over epsilon naught, that's just a constant. So on that side of the equation, so let me write it over here. On this side of the equation, as I take that limit, I'm just going to get 1 over epsilon naught. And now, the remaining pieces, think about what this is. This is the total charge inside the peanut. This is the volume of the peanut. So what I'm getting is the charge per unit volume in my peanut. Good. That's just charge density. We usually call that rho, right? The charge density rho. But the neat thing is, the way I'm taking the limit is I'm shrinking my volume down to this one mathematical point. I might as well give it a name. I'll call that point R. It's some location in space. I'm shrinking it down to that one specific point. As I do that, then, I'm getting the average density actually inside this peanut, but as it shrinks down to that one point, eventually I'm just going to get the value of the density at that point. So that's just the density at point R, the point to which I'm shrinking everything down, right? That's just what density means, basically. You take a tiny volume, you add up what's in it, you divide per volume, and you make sure your volume is near the point where you're trying to compute your density. Now, on the left-hand side, it's somewhat of a similar idea, somewhat of a similar process that's going on. Let's think about this. What are we doing? Don't worry so much yet about, this mathematical thing on the inside. The divergence of V might look a little scary to us at first. But whatever's going on, notice, mathematically, I'm taking some function, right? And I'm integrating it over volume, and then dividing by the volume that I integrated over. What is that the formula for? Just mathematically, if I do it for any function, if I take a volume integral over some volume v of some function, right, f at some location, right, over all the points inside my volume, dv, and I divide by volume, mathematically, here, I'm just thinking here a little bit on the side, mathematically, what is that the definition of? It's actually just the definition of the average value. Oftentimes we indicate average value by putting brackets of f, right? The average value of f in that volume. If that doesn't immediately jump out at you, remember you might be more familiar with this when you're looking at functions on a line. You might remember that if you integrate f of x dx, say from 0 to L, and divide that by the length L that you've just integrated over, that is in fact just the very definition of the, I don't know why it keeps doing that. It must be I'm on the very edge. That is the very definition of the average value of f. That's one dimension. Sometimes you might write that as average value with f with a little bar on top, right? That's just definition of average. You integrate over some region, divide by the side of the region, that's the average value. So, this whole right-hand side then, left-hand side, sorry, this whole left-hand side then becomes just the average value of the function I'm integrating, which is the electric field, the divergence of the electric field. But it's not just any average, right? We're taking this limit as we're shrinking our volume down. So it's the average value of the divergence, right, in this tiny little volume that's shrinking down to this one point. Well, just like with density, as I'm shrinking this average value down to this point, eventually I'm just averaging together all the stuff that's at that point. I just get the value at that point when I come to the final limit. So this is actually equal to the divergence of the electric field at that same point, R, to which I'm shrinking down my volume. And that, then, is a very powerful equation. This equation you can show, we're not going to right now, but you can show that this not only is a consequence of Gauss's law and the divergence theorem, right? It runs the other way around. I can take this and use the divergence theorem. I can basically substitute this equation into the divergence theorem and prove that the integral form of Gauss's law that you are used to actually follows from this differential form. The two are equivalent. And this is called usually the differential form of Gauss's law, comma, Gauss's law, or if you want, I like to call it tongue-in-cheek, Gauss's law 2.0. It's a very powerful Maxwell equation. And in a moment, I'm going to show you the various uses for it. I just want to, before I go into that, remind you what this divergence is. Because I know, the vector calculus can get a little bit rusty. But you might recall that the way we compute divergences, so if you want the divergence of the electric field E at some point, and here I was writing it as a vector, let me write it out very explicitly in terms of components. So say the electric field is a function of your three coordinates, x, y, and z. And I want the divergence of that. The way we calculate that, you might remember, is you take the partial derivative of the first component, the x component of the electric field, with respect to x, and then you add to that the corresponding term for the y component. You take the y component of the electric field and the derivative with respect to that component y, and then finally you have the third component, the z component of the electric field, the partial derivative of that with respect to z. You sum those three partial derivatives, x, y, and z, and that is the definition of the divergence. Now that we have this, this has two very useful uses. The first use is practical, And the second use is philosophical. So this is uses for the differential form, or Gauss's law 2.0. The first one is, it's a great way, if you look at the form of the equation, right? It's easier to work with than the integral form, right? If I want to use this equation, all that I really have to do is take some derivatives and add them together. That's a lot less work. That's a lot easier than doing some big, nasty surface integral, right? Like we had to do in our previous example here, right? There's all these steps to evaluating it. You get used to it, you get the hang of it, and it's sure as heck easier than Coulomb's law, but nonetheless, it can turn into a fair amount of work, and there's some thinking involved. In this case of the differential form, fortunately, we don't have to do a whole lot of thinking. We just kind of grind through. We do have to remember our partial derivatives, but we just take some partial derivatives and add them up, and then we get this interesting equation. Now, the use for it is kind of the backwards version of what we've been doing so far with Gauss's law, right? The Gauss's law that you've used so far, what you do is you take some charge distribution, right, and you use it to try to figure out the electric field knowing the charge. Well, the derivative is the opposite of the integral, so it makes sense then that the derivative form lets you do the opposite. Namely, instead of going from knowing the charges to getting the field, this allows you very quickly to go from the field in order to get the charges. So that tells you how to, if you know E, which, depends on your coordinates, then it's quick to get the density at any point, rho of r. If you look at the mathematical form we just had, you can solve this pretty quickly for rho, right? Just multiply through by epsilon naught. Rho of r is epsilon naught times, divergence, right, of the electric field at that corresponding point. So sometimes you might just want to know the density, and you might have been given the electric field for a situation. Well, this is a very quick way to get that density. Another thing it's great for is to check your answers, right? It's great to check your answer for E, right? Say you've done some big problem, and you finally computed the electric field, E of r. How do you know you didn't mess up? Well, just like in calculus class, the way you check to make sure you didn't mess up some integral is to go ahead and take the derivative. Well, here, to make sure you didn't mess up the integrals you used to get the electric field, you can just take the derivative of your answer and check that you get back the charge distribution that you were given in the first place. So it's a great check on answers for electric field. So that's the first use. That's the practical use. The second use is more philosophical. So this one was more practical. The second use is more philosophical, and it has to do with action at a distance. If you thought very carefully about how we resolved action at a distance, we kind of swept something under the rug. And a number of students in various discussions I've had, on Piazza or the other feedbacks that we get, kind of pointed this out if you're really closely paying attention. Remember what the original problem was? The original problem was if you have some charge Q1 sitting at some location and another charge Q2 sitting at some far away location from it, Q2, we know from Coulomb's law that Q1 is going to exert a force. If these were both positive charges, say, it would exert a force on Q2 across some distance of space R12. And Descartes, for instance, hated that kind of action at a distance. It makes no sense to him, and also in our modern field theory, that one object very far away from another can have an instant influence without, any direct contact. It violates all kinds of principles of relativity and causality. It causes all kinds of trouble. Now, we said that the answer to that, right, was not to think of the force on 2 due to 1, right, as sort of coming directly, as following directly from some law, Coulomb's constant, Q1, Q2. Here I'll write it in the R hat 2, 1. I'll write it in the trig form, R1, 2 squared, right? Said, no, we wanted to get away from that because that implies that you can have this force exerted over this distance instantaneously. Rather, we said that the force on particle 2 should be thought of as Q2 responding to a property of space at location R2. So it was Q2 times the electric field computed or measured at the location R2. So that way, the force that you're connecting to doesn't have to do with this far away distance thing. It has to do with the fact that there's something special about space, this electric field property, and Q2 is just responding to the electric field at R2, at the very location of Q2. And we said, well then, when we look at it this way, there's no action at a distance. That kind of, sweeps something under the rug. It does fit Descartes' view that, well, there's some Cartesian vortex here at Q2, right? There's some distortion of space, namely what we in modern days call the electric field in a field theory, right? And that's what's exerting the influence on 2. But that doesn't explain to us how Q1, right, can, over this large arbitrary distance, create this electric field, right? It seems, again, we have this instantaneous information traveling across this distance, right, without any direct intermediate contacts. So the problem, that was a half solution. The problem is when we think of the electric field at R2 as having this long-range formula, KCQ1 R21 hat divided by this long distance, R12 squared, that has action at a distance. So this is okay. But this has action at a distance. Now, Gauss's law in the integral form, this is Coulomb's law. Gauss's law in the integral form kind of doesn't solve the problem either, right? If I look at Gauss's law version 1.0, it is saying something like this. The integral of E dot dA, right, over some surface, which could be very far away from the enclosed charge. Somehow, this enclosed charge is reaching far across space, potentially, to have some influence on the electric field on some very far away surface. I could have some really huge surface here, light years across, and I have my enclosed charge, might be a point charge in here, but somehow that point charge is affecting the electric field vectors way out here, very far away. That looks potentially mysterious or dangerous also. The beauty, though, is this differential form, Gauss's law 2.0. If you look at the mathematical structure of this, we're saying the divergence of the electric field, right, the derivative of the electric field at a given location is just the charge density at that location divided by epsilon naught. What this means is the charge at location R is affecting the electric field really only at that location, or in fact, if you think about what this is a derivative, and neighboring locations. Remember how derivatives work, right? If I look at say, df dx, mathematically that is f at x plus some small little delta minus f of x divided by delta in the limit, of course, that delta goes to 0. Whenever I have a derivative, or any kind of partial derivatives, things that make up this divergence, I'm just talking about comparing this function, in this case the electric field, at neighboring points. So Gauss's law 2.0 doesn't have any action at a distance in it, right? It just says that the density affects the electric field at the given point and potentially neighboring points through the derivative. And then as I get to places where maybe there isn't any charge density anymore, where this term might be 0, right? It's again just relating the electric field at one point over towards a neighboring point. This allows the electric field at one point to affect neighboring points and for charges to affect neighboring points. And then maybe those neighboring points in the electric field to affect the next neighboring points, and those neighboring points the next ones, and the next ones the next ones, and so forth, down a chain of local interactions that don't go over a distance, no action at a distance, but eventually the electric field, through affecting neighboring electric fields, can have an influence very, very far away. So the Gauss's law 2.0, which has no action at a distance, yet it describes all of the phenomena that we are familiar with at a distance, allows us to resolve the action at a distance problem by this idea of modern idea of derivatives, just neighboring points affecting each other, corresponds precisely to Descartes' idea of vortices at one point, stirring up vortices at the next point, stirring up vortices at the following points, and so forth down a chain to make something that looks like a long-range interaction, but something which is really only one neighbor affecting the next neighbor affecting the next one. Okay, so that wraps up this set of notes. The next set of notes, we're going to start to look at things that are going to bring us a little less abstract from these action at a distance things, more practical issues. We're going to start to look at energy in electrical systems, which will take us very, very quickly into circuits. Thank you. We'll talk to you next time.